Good morning, students. I am Suneetha, Assistant Professor of Chemistry from Kakatiya Government College, Hanamkonda. Today I am going to discuss about aromatic hydrocarbons, where today's our subtopic is concept of aromaticity. Concept of aromaticity. Now, let's discuss aromaticity. So, what is meant by aroma? First of all, let us see. Aroma stands for sweet smell. So, compounds like benzene will have sweet smell, thus they are called aromatic compounds. But all aromatic compounds, they do not have a good smell or sweet smell. Then there must be some other criteria to define aromaticity. Generally, the source of aromatic compounds is petroleum. The source of aromatic compounds is petroleum. Because of that reason, these compounds, they will be having certain aroma. Now, if we consider benzene, benzene we know it is C6H6, which has three pi bonds, that is highly unsaturated compound, but it does not undergo addition reactions like unsaturated compounds. Benzene is it is an unsaturated compound, but it does not undergo addition reactions, whereas it undergoes substitution reactions. It undergoes substitution reactions. So, not only benzene and benzene-like compounds, which are called benzenoid compounds, they also undergo substitution reactions instead of addition reactions in spite of their highly unsaturated nature. So, these benzene and benzenoids and benzene-like compounds which are highly unsaturated but undergo substitution reactions are only called aromatic compounds, and this phenomena is known as aromaticity. So benzene and benzene-like compounds, that is benzenoids, they though they contain highly unsaturation, but they undergo substitution reactions instead of addition reactions are called aromatic compounds, and this phenomena to exhibit such type of behavior is known as aromaticity. It is known as aromaticity. So this is about concept of aromaticity. So aroma stands for sweet smell. Compounds like benzene will be having certain sweet smell, characteristic smell, let me say, that is pungent smell they have, and which are known as aromatic compounds. But there are many compounds, many aromatic compounds which do not show good smell. So because of that reason, there is a need to define aromaticity in terms of some other concept. That is, in this way we can discuss that benzene and benzenoids, they, in spite of having high unsaturation, they do not undergo addition reactions, whereas they undergo substitution reactions. Thus, these compounds are called aromatic compounds, and this concept is known as aromaticity. This concept is called aromaticity. Okay. Now, to explain aromaticity, Haeckel, he proposed one rule that is known as Haeckel's rule. According to Haeckel, planar monocyclic ring compounds containing pure p orbitals with 4n plus 2 pi electrons, they act as aromatic, or they are aromatic compounds, where n is an integer which is equal to 0, 1, 2, 3, so on and so forth. Okay, so as per Haeckel, any planar monocyclic ring compounds or cyclic ring compounds, instead of mono we can say cyclic compounds containing pure p orbitals with 4n plus 2 pi electrons act as aromatic compounds, where n is an integer which is equal to 0, 1, 2, 3, etc. So Haeckel's rule is based on quantum mechanics. Here let us consider one example, that is benzene. Okay, example benzene. So benzene is an aromatic compound. In this, n is equal to 1. Benzene has 3 pi bonds, which is equal to 6 pi electrons. Applying Huckel's rule, that is 4n plus 2. 4 into n equals to 1, that is 4 into 1 is 4 plus 2 is 6. So 4 into 1 plus 2 equals to 4 plus 2, that is equal to 6 pi electrons. As benzene has 6 pi electrons, it has 3 pi bonds, why not? 6 pi electrons. It is obeying Huckel's rule. Therefore, benzene is said to be an aromatic compound. Benzene is said to be an aromatic compound. Okay. Now, let's discuss some other points about Huckel's rule. About Huckel's rule. Okay. Now, the planar monocyclic ring compounds with 2 electrons or 6 electrons or 10 electrons or 14 electrons, so on and so forth, with delocalized pi electrons should be aromatic as per Huckel's rule, and they obey 4n plus 2 rule. Okay. According to Huckel, the planar monocyclic ring compounds with 12 or 6 or 10 or 14 pi electrons, 14 delocalized pi electrons, should be aromatic as per Huckel, and they obey 4n plus 2 rule. They obey 4n plus 2 rule. And these compounds will have pi electron clouds above and below the plane of the ring. All these compounds, they have pi electron density above and below the plane of the ring, and these systems will have closed delocalized electrons in the ring, and they will have substantial resonance energy. Okay, so these systems with the closed delocalized electrons in the ring, then what happens? Because of the closed ring system, they will be having considerable resonance energy. When the resonance energy is more, then what happens? The system becomes stable. Greater the resonance energy, the greater will be the stability of that particular compound. Therefore, due to delocalization of this pi electron density, the system will be having considerable amount of resonance energy. Therefore, these substances are said to be stable. Okay. Now, let's consider one example. Here we have discussed just now. Benzene, it has 6 pi electrons. According to molecular orbital theory, 6 pi electrons will be filled in bonding molecular orbital. Bonding molecular orbital. And here we can see the energy profile. That is, bonding molecular orbitals will be having lower energy than non-bonding molecule than the non-bonding orbitals, and non-bonding molecular orbitals will be having lesser energy when compared to anti-bonding molecular orbitals, ABMO, NBO and MBO. This is bonding molecular orbital, bonding molecular orbitals, BMO or MBO. So bonding molecular orbitals will be having lesser energy than non-bonding, which have lesser energy than anti-bonding molecular orbitals. So this is the increasing order of the energy from here to here. Okay. Now let us see this benzene. It has 6 pi electrons, and these electrons are filled in bonding molecular orbitals. Bonding molecular orbitals. This side. Okay. Then these bonding molecular orbitals, as they have lesser energy, they have high stability. Because of that reason, this benzene is said to be aromatic, as it is obeying Huckel's rule. It is having 6 pi electrons. It obeys 4n plus 2 pi electrons rule, that is Huckel's rule. And all these 6 pi electrons are filled in bonding molecular orbital, which has lesser energy or lower energy, and thus it will be having high stability. Hence, this benzene is said to be an aromatic compound. This is the first example for aromaticity. Now, second example, cyclooctatetraene. You can see cyclooctatetraene, cyclic compound. Octa means 8 carbons are there. Tetra means 4. Ene means double bonds. So, 8 carbon ring system which has 4 double bonds. Okay, 4 double bonds in the sense which has 8 pi electrons. 8 pi electrons. So now if we consider this cyclooctatetraene, 6 pi electrons are present in the bonding molecular orbital and 2 unpaired electrons are present in the non-bonding molecular orbital. Okay, 2 unpaired electrons are present in the non-bonding molecular orbital. So here non-bonding molecular orbital, right? Because of this, which has more energy and less stable when compared to benzene, this has more energy and it is less stable, and it becomes this cyclooctatetraene is a non-planar molecule and which is non-aromatic. It has 8 pi electrons. 6 pi electrons are present in bonding molecular orbital. 2 pi electrons are present in non-bonding molecular orbital, which is they are unpaired electrons. And because of the presence of 2 unpaired electrons in non-bonding molecular orbital, it has more energy and less stability, and it is not at all a planar molecule. Because of that reason, this molecule is said to be non-aromatic. It is non-aromatic molecule. Okay. Right. Now next see the another example. This is pyrrole. Pyrrole. This one. This is a heterocyclic compound. That is heterocyclic compound in the sense the ring system should contain one or the more hetero atoms like nitrogen or oxygen or sulfur, etc. Then it is said to be heterocyclic compound. So this is the best example, simplest example for heterocyclic compound. This is pyrrole. This is pyrrole. So here CH, 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 CH and NH. Okay. So this is pyrrole. And this pyrrole has, you can see, 2 pi bonds, that is 4 pi electrons. See, 4 pi electrons. And a pair of electrons, you can see a pair of electrons on nitrogen atom. A pair of electrons also present on the nitrogen atom. So altogether, it is a planar monocyclic heterocyclic compound which obeys Haeckel's rule, that is 4n plus 2 pi electrons rule, because it has 4 pi electrons from the 2 pi bonds and 2 electrons, that is non-bonding pair of electrons which are present on nitrogen atom and nitrogen atom. So altogether 6 electrons are present. Because of that reason, this molecule is also aromatic because it is obeying 4n plus 2 rule of Haeckel. So according to Haeckel's rule, any monocyclic planar ring system containing 4n plus 2 pi electrons is said to be an aromatic compound. Therefore, this has 6 pi electrons. Therefore, this pyrrole is also an aromatic compound. Now, next example is naphthalene. Okay, naphthalene. Naphthalene, it is a planar bicyclic compound, and which has 5 bonds. You can observe 1, 2, 3, 4, 5 pi bonds. Therefore, as it is having 5 pi bonds, it should be 5 bonds. It has 10 pi electrons. 10 pi electrons. Okay, 10 pi electrons. And here n is an integer which is equal to 2. Therefore, 4 into 2 is 8. 8 plus 2 is 10. Therefore, if n is equal to 2, 4 into 2 plus 2, that is 8 plus 2 is equal to 10 electrons. So, because of this one, this naphthalene is also said to be an aromatic benzenoid compound, as it is also obeying 4n plus 2 pi electrons rule of Haeckel. So, according to Haeckel's rule, any uh, planar ring system containing 4n plus 2 pi electrons is said to be aromatic. So here this is naphthalene. Naphthalene is also obeying Haeckel's rule, thus it is an aromatic compound. So totally it has 10 electrons. It has 10 electrons. Okay, 10 electrons. That is 5 bonds, which is equal to 10 electrons. Therefore, it is obeying 4n plus 2 pi electrons rule. Thus, it is an aromatic compound. Next one, let's see this. Okay, this is anthracene. Sorry, it should be anthracene. Okay, so anthracene, this is anthracene. This anthracene is having 3 benzene rings fused linearly. 1, 2, 3 benzene rings fused linearly with 7 pi bonds. 1, 2, 3, 4, 5, 6, 7. 7 pi bonds, that is 14 electrons. And this polycyclic ring compound is aromatic with 14 electrons. As per Haeckel's rule, it is also having 4n plus 2 pi electrons, that is equal to 4 into n is equal to 3 here. N is not equal to number of rings, so you should remember that point. Okay, n is an integer, it is not equal to number of rings. Some of the cases it may be equal to number of rings, but always it is not the so. Okay, so where n is equal to 3, so 4 into 3, that is 12 plus 2 14. So 12 plus 2 14 electrons it has, therefore it is also said to be an aromatic compound. Next one, this is also a 3 benzene rings. Here also we have, this is known as phenanthrene. The name of this compound is phenanthrene. Phenanthrene, Threne. Threne. Phenanthrene. Some spelling mistake is there. Phenanthrene. This is also has 1, 2, 3, 4, 5, 6, 7. 7 pi bonds, that is 14 electrons. So like anthracene, it is also having same 3 benzene rings, but in the anthracene molecule we have seen 3 benzene rings are attached in a linear manner. Am I right? In a linear manner. But here the benzene rings are, the arrangement of benzene rings is a little bit different. Okay, so this is also aromatic according to Haeckel's rule, because it is also having 14 pi electrons. 14 pi electrons. So that is 4 into 3 is 12 plus 2. That is, it has 14 electrons. 4 into 3 is 12 plus 2 14. So it has 14 pi electrons. Therefore, it is also said to be an aromatic compound where n is equal to 3. N is an integer which is equal to 3. So these are all aromatic compounds except cyclooctatetraene. Cyclooctatetraene, as it is a non-planar molecule which is non-aromatic. Now, let us see some of the non-benzenoids, that is, which do not have benzene-like structure or properties. Benzene like ring is not there, then they are called non-benzenoid compounds. Let us consider some of the non-benzenoid compounds which are also aromatic in nature. So there the first example is cyclopropenyl cation. Okay, cyclopropenyl cation, C3H3 plus. So this cyclopropenyl cation here, cyclopropenyl cation, this 1 carbon, 2 carbon, 3 carbon. Okay, here it has 1 hydrogen, it has 1 hydrogen here, and here also 1 hydrogen. Okay, so cyclopropenyl cation, if 2 hydrogens are there here, then it is known as cyclopropene. From that, 1 hydrogen is removed, 1 H minus is removed. Okay, not proton. Then it becomes cyclopropenyl cation. Now this cyclopropenyl cation, which is a planar molecule, which is triangular, shape we can see triangular planar molecule, okay, with one pi bond that is equal to 2 electrons. When n is equal to 0, n is equal to 0, it is substituted in Haeckel's rule, that is 4n plus 2 pi electrons. Then 4 into, it should be 0. 4 into 0, this is 0. Okay, 4 into 0 is 0 plus 2. That is 0 plus 2 is 2. So as it is having 2 pi electrons, it is obeying Haeckel's rule, which is non-benzenoid compound. It is said to be aromatic. Okay, so this is cyclopropenyl cation, which has 2 pi electrons. If we substitute this, if we apply Haeckel's rule to this particular cyclopropenyl cation, then what happens? 4n plus 2 pi electrons. Therefore, n is equal to n is 0. N is an integer, it should be taken as 0 in this case. Then what happens? 4 into 0 is 0 plus 2, that is 2 pi electrons it has. As it is having 2 pi electrons, it fits into it, obeys, it follows Haeckel's rule. Therefore, it is said to be an aromatic compound. And let's see the different resonance structures of cyclopropenyl cation. Due to the presence of these resonance structures, this particular cation is stabilized. See this, if this pi bond shifts towards this, then what happens? We will get a positive charge here. Okay, then shift of pi bond towards this, then we will get a positive charge here. You can see this one. Okay, like this on all the 3 carbon atoms, here, here and here, all the 3 carbon atoms positive charge is there, that we can show it like this. Okay, so this is cyclopropenyl cation, which is said to be aromatic because it follows Haeckel's rule, and it is a cyclic planar molecule. Cyclic planar molecule which follows Haeckel's rule. Okay. Let's consider the next example, that is cyclopentadienyl anion. Cyclopentadienyl anion. So this has a planar structure, cyclopentadienyl anion, okay, which has the planar structure with you can see 2 pi bonds here, and anion means a negative charge that indicates 2 electrons. So altogether 6 electrons are present. So 2 pi bonds, that is 2 into 2, 4 pi electrons, and it has one negative charge that is equivalent to 2 electrons. Therefore altogether 6 electrons are present here. Okay, so cyclopentadienyl anion, which has planar structure with 6 electrons, that is 4 from 2 pi bonds and 2 non-bonded electrons. This one, non-bonded electrons. Okay, so this molecule, it also obeys Haeckel's rule and it is said to be aromatic compound. See, 6 electrons means 4 into 1 plus 2, where n is equal to 1. Okay, 4 into 1 is 4 plus 2 is 6 electrons. As it has 6 electrons, it is said to be aromatic because it is obeying Haeckel's rule. Okay, it is obeying Haeckel's rule. And here this molecule, it has this negative charge which is present on this carbon. It will be in the resonance with pi bonds, which gives more stability to the molecule, to this particular ion. Okay, this is the negative ion. So due to the presence of this resonance structures, the molecule gets more stability. Okay, you can see the different resonance structures of cyclopentadienyl anion. So it is a cyclic planar molecule which has 6 pi electrons, obeys Haeckel's rule, and which is stabilized by resonance. Thus, it is aromatic compound, and the resonance is due to the presence of negative charge. This negative charge will be in resonance with the pi bonds, giving this particular ion more stability. Okay, now let's discuss another example. This is tryptophan cation. Tryptophan cation. C7H6 plus. C7H6 plus tryptophan cation. This tryptophan cation is also called 1,3,5-cycloheptatrienyl cation. 1,3,5-cycloheptatrienyl cation, as it has three triple bonds. Okay, 1,3,5 cyclic compound. Hepta, 7 carbons are there. Tri means three double bonds, three pi bonds. Enyl, en means double bonds. Tri means three, en means double bonds. This is a cation. Therefore, it is 1,3,5 cycloheptatrienyl cation, and it is said to be aromatic compound because it obeys Haeckel's rule. It also obeys Haeckel's rule. So, according to Haeckel's rule, it should have either 2 or 6 or 10 or 14 and so on and so forth pi electrons. Any molecule, cyclic planar molecule having those many pi electrons is said to be aromatic according to Haeckel. Now it has 3 pi bonds, that is 6 pi electrons. It has 3 pi bonds, that is 6 pi electrons in a single planar molecule, that is, and it also has conjugated double bonds. Conjugated in the sense alternate double bonds it has, and this will be, these double bonds will be in the resonance with the positive charge. They are in resonance with the positive charge in the ring. Because of that reason, it will be having different resonance structures. As more the number of resonance structure, more is the stability. As this cation is stabilized by resonance due to the presence of positive charge and pi bonds in the ring system, and it obeys Haeckel's rule, it is said to be aromatic. It is said to be aromatic. So it is obeying Haeckel's rule. The pi bonds, the conjugated double bonds will be in resonance with the positive charge, and it has 6 pi electrons. Therefore, it is aromatic. So this is very, very important. You should remember. Generally, this will be asked in different examinations. Tryptophan cation. So tryptophan cation is aromatic compound, and it is also known as 1,3,5-cycloheptatrienyl cation. 1,3,5-cycloheptatrienyl cation. Okay. Right. Now next, let us consider the preparation methods of this benzene or benzenoid compounds. So for this aromatic compounds, the simplest example and the best example is benzene. So here we are considering the preparatory methods of benzene. So different preparations of benzene. Let us consider that. The first one is from acetylene. So from acetylene, how benzene is prepared? Let us see. As what is acetylene? Acetylene is an alkyne, the simplest alkyne. The first member of alkyne series, CH triple bond CH or C2H2. C2H2, that is acetylene. When this acetylene gas, it is in the gaseous state. When this acetylene gas is passed through red hot copper tube. Red hot copper tube. So copper here is the catalyst, red hot copper tube. Then what happens? Benzene is formed due to polymerization or trimerization, let me say. Okay, trimerization of acetylene. So 3 moles of acetylene. Okay, they form 1 mole of benzene, C6H6. 3 moles of C2H2 gives rise to C6H6. So this is called trimerization or polymerization of acetylene. So when acetylene gas is passed through red hot copper tube, then what happens? We get benzene. We get benzene. So you can see the formation of benzene from acetylene. So this is CH triple bond CH, one molecule of acetylene. This is another C2H2, another molecule. Here one more molecule of C2H2. Now you can see the bond formation. Now benzene is formed. Benzene is nothing but C6H6. Okay. So here we can write it like this. This is about the preparation of benzene from acetylene. Now let's consider another preparation of benzene. This is preparation of benzene from phenols. So from phenols, how benzene is obtained. So phenols, when they are reduced with uh, zinc dust, zinc dust, then we get benzene. So benzene is formed when vapors of phenol are passed over heated zinc dust due to reduction. So benzene, it is obtained due to reduction of phenol. So how this phenol is reduced? When phenol is vapors of phenol when passed over heated zinc dust. This is delta heating zinc dust. Okay, this zinc, what it will do, it removes this oxygen from phenol. That is, removal of oxygen is nothing but reduction. Therefore, we get benzene. Other product is ZNO. Is it okay? So this is preparation of benzene from phenols. Now let's see the next preparation of benzene. So from benzene carboxylic acids. So from benzene carboxylic acids or the salts of the carboxylic acids, we can prepare benzene. So let's see the preparation of benzene from benzene carboxylic acids. So aromatic acids and their sodium salts, either acid or its salt, sodium salt. On heating with soda lime is a mixture of sodium hydroxide and calcium oxide. This is soda, caustic soda, NaOH. Lime is CaO. So the mixture of these two is known as soda lime, and soda lime is a decarboxylating agent. We know this. So what it will do? It removes CO2, decarboxylating agent. Okay, it removes CO2. So because of that reason, it is known as decarboxylating agent. And aromatic acids and their sodium salts, they, on heating with soda lime, they produce benzene. You can see the reaction here. This is sodium benzoate, sodium salt of benzoic acid. C6H5COOH is benzoic acid. From that, H is replaced by Na, then it is sodium salt of benzoic acid, which is called sodium benzoate. When the sodium benzoate, it is heated with the soda lime. Then what happens? This Na2, and this C plus two oxygens, and this oxygen CO3. Na2CO3 is lost. And this H, here, we get benzene. Okay. So this is preparation of benzene from benzene carboxylic acids or its salts. This is another preparation. Now let's see the one more preparation of benzene. This is benzene preparation from benzene sulfonic acid. From benzene sulfonic acid, how benzene is obtained. So benzene sulfonic acids, when subjected to hydrolysis, when they are subjected to hydrolysis by superheated steam or by boiling with dilute hydrochloric acid under pressure at about 400 to 470 Kelvin temperature, we get benzene. Okay, so this is benzene sulfonic acid. This benzene sulfonic acid, when it is subjected to hydrolysis, that is hydrolysis by superheated steam, or by heating or by boiling this with dilute hydrochloric acid under pressure at about 400 to 470 Kelvin temperature, benzene is the product obtained. You can see the reaction here. This is benzene sulfonic acid, C6H5SO3H, when it is subjected to either hydrolysis with steam or by boiling with dilute HCl. Okay, dilute HCl, we get benzene as the product. These are the four preparations of benzene. One is from acetylene, second one is from phenols, third one is from benzene carboxylic acids or its sodium salts, and fourth one is from benzene sulfonic acids. Okay. Now let's see the chemical properties. Benzene and benzenoid compounds. Benzenoid compounds means benzene-like compounds. Okay. So benzene and other benzenoid compounds, they generally undergo electrophilic substitution reactions. Electrophilic substitution reactions. Okay. And let us consider the general mechanism of this particular electrophilic substitution reaction. What is electrophilic substitution reaction? It's a substitution reaction in which is initiated by an electrophile. It is a substituted reaction which is initiated by an electrophile. That is, an electrophile, it substitutes one of the hydrogen atoms of benzene. That is one electrophile, let me say. An electrophile substitutes another electrophile. Then it is known as an electrophilic substitution reaction. Now let's see this general reaction. PHH. PH is phenyl group. Phenyl is C6H5. So C6H5 and H, that is C6H6. This is benzene. Okay. When it is treated with a reagent, here is a reagent. So E stands for electrophile and other part of that reagent is A, that is nucleophilic part, let me say. Okay. Then what happens? From this benzene, this hydrogen is replaced by this electrophile. Then we will get PHE. You can see substituted benzene. Okay. Other product is this H along with this A, nucleophilic part of this particular reagent, and this H, that is electrophile. We will get HA. Now we can also show the same reaction like this. Okay. This is benzene, C6H5 and H, that is C6H6. All carbon atoms of benzene ring, they have hydrogens, but here we have shown only one hydrogen because our point of interest here is electrophilic substitution. So an electrophile is substituting one of the hydrogens, so we have shown here. Otherwise, all this carbon, this carbon, this carbon, all the six carbons, they have hydrogens, but we did not show. Okay. So then what happens? This benzene, when treated with a reagent, the electrophilic part of the reagent, it substitutes this hydrogen and we will get a substituted product. Okay, substituted product, substituted electrophilic substitution. This is electrophilic substitution reaction in which an electrophile substitutes one of the hydrogen atoms of benzene ring to give a substituted product. This is, and this H, it goes with the nucleophilic part of the reagent to give another product, byproduct. Let's discuss the reaction mechanism for this particular electrophilic substitution reaction. Okay. Now here electrophiles, generally they are positively charged species and sometimes electron deficient compounds, they also act as electrophiles. Though they do not have a positive charge, if they have electron deficiency in the molecule, then also they act as electrophiles. So electrophiles are either positively charged species or electron deficient compounds. Okay. So generally these electrophiles are represented by either E or E plus or E with an empty orbital. E with empty orbital. Okay, because it is electron deficient compound. Okay. Now, what happens here? Let us see. As benzene has 6 electrons, that is 6 pi electrons. Okay, that is because of the presence of pi electron cloud, it acts as a nucleophile. Okay, pi electron cloud, it acts as a nucleophile and it allows electrophilic attack on the pi bond. Then what happens? An unstable intermediate is formed without aromatic nature. An unstable intermediate is produced without aromatic nature, which is called a sigma complex, And this non-aromatic carbocation, that is sigma complex, is a carbocation. This is non-aromatic. Non-aromatic sigma complex or non-aromatic carbocation. It is stabilized by resonance. As the more the number of resonance structures, more is the stability. As the sigma complex is stabilized by resonance, it is easily formed. It is easily formed. Now let us consider this. This is benzene. It has 3 pi bonds, that is 6 pi electrons. It acts as a nucleophile due to the presence of excess of electron density. And from the reagent, this electrophile, this pi bond, it abstracts pi electron pair. It abstracts this electrophilic part of the reagent. Then what happens? Here you can see already one hydrogen is present on this carbon. Now another bond is formed on this particular carbon with the electrophile. Then what happens? You as this pair of electrons, that is this pi bond, it forms a bond with this electrophile. This carbon, it possesses now a positive charge. And this ring electrons, pi electron density present in the ring, it will be in resonance with the positive charge. Thus we have such type of resonance structures different resonance structures. Okay, now these are all these structures are called benzenonium ions. These are called benzenonium ions. Benzene em means positive charge. On benzene ring, em positive charge is present. Therefore, these are called benzenonium ions, and which is also called a sigma complex. It is also called a sigma complex. Now, here the electrophile, it forms a sigma bond breaking a pi bond. Here, this electrophile, it forms a sigma bond breaking a pi bond. This pi bond is broken and a new sigma bond is formed. Okay, so this electrophile, it forms a sigma bond, new sigma bond breaking a pi bond, that is sp2. We know all the carbon atoms in benzene are sp2 hybridized, okay, leading to the formation of a sigma complex which is sp3. So here, before the formation of a bond with the electrophile, it is sp2 hybridized. All the 6 carbons are sp2 hybridized. But in this sigma complex, this carbon is sp3 hybridized. We know in the sp3 hybridization, around surrounding the carbon, all the 4 single bonds must be there. You can see all the 4 single bonds are present. Therefore, it is sp3 hybridized carbon. Okay. So, here electrophile, it forms a sigma bond breaking a pi bond, that is sp2 hybridized carbon becomes sp3 hybridized carbon in the sigma complex, and this 4 pi electrons in the sigma complex. You can see 4 pi electrons, that is 2 pi bonds means 4 pi electrons are delocalized in rest of the 5 p orbitals of other carbocations. See, you can see here. So this pi bonds, they are delocalized because of the presence of uh, carbon atom, different carbon atoms present in the ring. Okay, so this positive charge is delocalized due to the presence of 4 pi electrons here, and as this positive charge is in delocalization with the 4 pi electrons present in the sigma complex, this will be having the more number of resonance structures. As the number of resonance structures increases, the stability of sigma complex is also increased. Okay, so now let us see the continuation of this one. Uh, the next step, what happens? The sigma complex, it releases one proton, that is H plus, from sp3 carbon, from sp3 carbon, which is attacked by electrophile, and it regains the aromaticity. So here you can see this sigma complex, it loses this H plus. It loses it H plus to the nucleophilic part of the reagent, that is A minus. Then HA is formed, and as it loses this proton and this bonded pair of electrons, they move towards these two carbon atoms. Thus a pi bond is formed here, and it retains its or it regains its aromaticity. You can see 6 pi electrons once again in this. Therefore, it is once again aromatic, whereas this sigma complex is non-aromatic. Okay, whereas this is aromatic. So it is non-aromatic compound, where this one after the abstraction of electrophile, this sigma complex, it is non-aromatic, where because of the presence of only 2 pi electrons. But this one, after the loss of proton from this, it becomes aromatic compound, substituted aromatic benzene. Okay, so substituted aromatic compound is once again obtained here. So now let's see the overall reaction. So electrophilic substitution reaction, overall reaction, there are two steps involved. Though in the overall reaction, it has two steps. Two steps. In the first step, what happens? An electrophile, this benzene ring, it forms a bond with an electrophile with the help of one of the pi bonds. Then what happens? A sigma complex is formed. This is the step one. Okay, this is the step one. Okay, this is a slow step, first step, which is a slow step, that is RDS. RDS means rate determining step. Okay, in the rate determining step, what happens? Benzene, it forms a new sigma bond with the electrophile with the help of one of the pi bonds. Then a sigma complex is formed. The sigma complex is stabilized by resonance. Okay, then in the next step, the sigma complex, it loses one proton from this particular sp3 carbon to the negative part, that is nucleophilic part of the reagent, to form the substituted benzene, and this is the second step of the reaction, which is a fast step, which is a fast step. Okay, so this is about aromaticity. Now let us see the important questions related to this particular topic. Okay, so there the first one is, what is aromaticity? Explain Haeckel's rule. This you can easily do it. Next one, explain aromaticity of tropylium cation. We have discussed just now. Now explain the aromaticity of cyclopentadienyl anion. This also we discussed. Next one, explain the aromaticity of benzenoid compounds with suitable examples. Many benzenoid compounds we discussed: benzene, naphthalene, phenanthrene, etc. Next one, explain aromaticity of non-benzenoid compounds. Non-benzenoid compounds here, tropylium cation, cyclopentadienyl anion, cyclopropynyl cation. These are all non-benzenoid compounds which are aromatic. And next one is, how is benzene prepared from benzene carboxylic acids? Just now we have discussed. Next one is, give preparation of benzene from phenol. How a phenol is converted to benzene, that is reduction of phenol with zinc dust. Okay, next one is, how is benzene obtained from acetylene? Acetylene gets converted to benzene when it is passed over heated copper tube. Okay, heated copper tube. So that is nothing but a trimerization of acetylene or polymerization of acetylene. It forms benzene. Okay, so these are all the different questions we come across from the topic which we have covered. Okay, right. Thank you all, and we will discuss the rest of the topic in the next session. Thank you once again.